All right, thank you for this kind introduction, and I really want to thank the organizers for putting this this wonderful webinar series together. We just talked about how this could continue, and I wanted to thank everyone for joining this morning. I will be talking about really a new dimension in optical nano-probe imaging in spectroscopy, where the scanning probe tip, which in conventional tip-enhanced and scattering type near-field imaging really interacts with the material weakly. So we have weak optical and small perturbations. And what I will discuss is an area we have entered only very recently, where we have noticed that we can actually localize and take advantage of this tightly confined near-field light-matter interaction to drive the system into a light-matter hybrid state based on this nano or pico-cavity. And I will demonstrate this at the example of the interaction and achieving strong coupling at room temperature with a single emitter here in the form of a quantum dot. And then I will show you how we were able to extend this work into probing the coupling of vibrational excitation in molecular matter with then coherent driving infrared radiation. So this has been really an exciting area for us, and we have been fortunate to have a number of great collaborators who were assisting us on the way, notably on both theory with Felipe Herrera and Sandeep Sharma, and on the experimental side with Matt Pelton and Sang-Young Oh, who has been previous presenter in this meeting, and Hatis Altuk. And I really want to acknowledge a number of very dedicated current and previous graduate students and postdocs. Recently, we've been joined by Roland Bilken, and graduate students Sam Johnson and Ben Wetten are working in this field. And much of the results which I will present have actually been accomplishments by Jun Nishida and Kyung-Duk Park, who are now faculty in Japan and Korea, as well as Eric Miller, who's now at Colgate University, and Molly May, who's a postdoc. So the atomic force microscope and scanning tunneling microscope, as you probably all know, provides atomic resolution, yet with limited spectroscopic information. Yet in combination with light, through this near-field interaction, it really then provides a form of quantum state result spectroscopy of materials. And the really underlying process is that as we combine this excitation, then also this broadband and ultra-short laser pulses, we can probe into these elementary lengths and timescales of lattice and electronic excitations as they define a lot of material properties. And this has been one of the main interests of our work in applying this method, and then with a broad range of optical modalities, including linear and inelastic, but also nonlinear and coherent interactions. The key attribute really is this near-field localization and then the associated momentum state of light, which far exceed the far-field plane wave momentum. And this is really what enables us to achieve super resolution imaging, in fact, with all optical modalities, where the spatial resolution is completely wavelengths independent and solely determined by the tip apex radius. But also these high momentum states in the near field really correspond to what you normally can achieve only with X-rays. So you really have X-ray momentum at optical frequencies, as a result of which you actually get a modification in actually extension of optical selection rules. And this really then allows also to enhance and control the light matter interaction. And this is just sort of a facet of the many material systems and scientific questions we can address. We can also do this in a multimodal combination of different optical modalities probing simultaneously, then also take advantage of how the tunneling current and its modification and also force interaction can induce strain and sample bias and other combinations which allow us to study these materials. But what all these applications have in common, whether we really study quantum materials or whether we study molecular and soft matter, also, even if we go into strongly perturbing ultra-fast pulse excitation, in all these systems, this is a weak perturbation in the sense that we are exciting quantum states, but without really modifying the quantum states itself. And what has always intrigued us is really, as we are analyzing these new optical selection rules, and then also we're looking for new optical physics in the near field, was the question whether and to which extent then the modification of the local electromagnetic density of states in this tip nano confined field actually matters and could really induce processes which are not readily available in far field excitation. And examples are that we noticed in thermal near field radiation that we actually get emission which is spectrally very distinct from far field black body emission. And also in optical forces, looking at the Casimir and Casimir polar forces as an indication that actually cavity QED effects play a role. And so this intrigued us to answer the question really at the bottom of our laundry list here of things we wanted to explore, whether we can actually achieve the strong coupling regime where we would hybridize the light field with the matter state. And what gave an indication is actually work which started by a graduate student now working actually for FEI and Intel, electrical engineering student who more than 10 years ago has really thought more about the antenna load interaction at optical frequencies, so approaching this coupling of this localized near field with a quantum state from an electrical engineering and antenna perspective. And this is where we noticed that in addition to simple questions of field enhancement and spatial localization, that we actually have density of states effects. And these density of states effects would actually inspire then the question whether in the strong light matter interaction regime, which is driven primarily by the mode volume, whether we can actually transition from this weakly coupled interaction to strong coupling. So this has been discussed multiple times in this seminar series, but let me just recap that the weak coupling really results in spontaneous decay of a quantum emitter at a rate which is accompanied by the emission of photons. And this gives rise then to a reduction of this radiative lifetime by what is called the Purcell factor. But if you want to achieve a continuous coherent interaction between the photon field and the cavity, this is possible only if this coupling rate and this interaction rate exceeds all losses of the system, both radiative and also intra-system non-radiative relaxation pathways. And if you reach that point, this is then where you will observe Rabi oscillation as a result of this light matter hybrid state, which corresponds in frequency domain to a mode splitting. And so this is dictated, this Rabi frequency, by the mode volume. So conventionally, the mode volume is determined by the diffraction limit. And then as you go to nanoscopic mode volumes in the near field, you can imagine achieving Rabi frequencies, even in the presence of strong dissipation. And two key driving factors here when we look in condensed phase systems is that what determines the Rabi frequency is the relaxation times of the system of the emitter as well as the transition dipole moment. So looking at electronic transitions, which have traditionally been studied, you have large transition dipole moments, but you generally have very short decoherence times in condensed phase systems. And in contrast, in vibrational transition, and this is what I will talk about in the second part of this talk, we actually have much smaller transition dipole moments. So it's much harder to get into the strong coupling regime, but we have much longer coherence times. And so the question is whether this can offset the challenges which arise, especially when we want to push the strong coupling into the single emitter regime. And this is really a key goal to do this at the single emitter level, including the single photon level and the coupling. And this is really one of the hallmarks in modern quantum technology as it's realized in systems like these with applications for quantum memories or to store quantum information, where the cavity-enhanced light-matter interaction allows then for this quantum state to be stored and then received on demand out of this quantum memory. Other applications are really how you do quantum state transduction, which you want to do is high efficiency, where you want to use systems like these then to transduce quantum information between qubits and quantum memories. So conventionally in these systems, you have to go to very low temperatures in order to dissipate, in order to reduce the dissipation pathways. And so operating typically at millikelvin to Kelvin temperatures then allows you to reduce the dissipation to the level that even with the modest coupling strengths you can achieve in these cavities because of their large mode volume, you can actually achieve strong coupling. And this is really a maturing technology. And what has been much discussed also in this webinar series is then to achieve much of the same goals, yet with sort of metallic nano and pico cavities, which are by their nature extremely lossy. So we have very low Q factors. The emitter is lossy, and we have these very small mode volumes, which are about 1 million times smaller than what you can achieve in these systems. And this would allow you then to potentially even achieve strong coupling of a single emitter at the single photon level, even at room temperature. And this, of course, is still an exploratory technology. But then we conceived the idea that whether we can actually achieve this in a very controlled way, where we use this very small mode volume in tip-enhanced spectroscopy, where then this plasmonic tip serves as the optical antenna, which confines the radiation field to this pico-cavity regime. And so we want to look whether we can achieve single emitter coupling and doing this at room temperature. So the analog in strong coupling achieved with plasmonic nanostructure has also been presented in this meeting by several previous speakers, where you want to control the mode volume with plasmonic nanoparticles. And we want to extend this approach with the idea that we can use the plasmonic nanotip then as a tool to also image. Through tip sample distance control, we can control the mode volume. But then also a very key attribute is that in all these systems, in addition to the emitter experiencing slight variations in local chemical environment, but also each of these plasmonic nanostructure emitter systems is different, both from the plasmonic structure as well as from the emitter. If we do this in the scanning probe configuration, then we can probe different emitters, but always with the same cavity. This idea was in fact conceived or promoted then initially by an approach using slot antennas in Bert Hecht's group. But here the confinement appeared to be too limited. And so the spectra were actually confusing, and it wasn't quite obvious how to interpret. Another challenge has been, and this is work which Matt Pelton highlighted, is that there has been a lot of confusion in prior work where one has to clearly distinguish whether one looks at a coherent scattering or incoherent photoluminescence emission, where peak splitting is not always a clear signature of strong coupling and can be obfuscated really by phonointerference and other effects. And so it's very important to have very clear metric to be sure that one is in the strong coupling regime and in fact also probes a single emitter. So the way we do these experiments is that we take a metallic, typically a gold metallic tip in a scanning probe configuration, manipulated with an atomic force microscope, typically in a shear force interaction, which allows then the control of the tip sample distance, actually which near atomic precision. We choose quantum dots. They have been fabricated in Matt Pelton's group and collaborators. These are core shell quantum dots, which are protected by a very thin aluminum coating, distributed on the mirror metal substrate. And here's typical spectral characteristics of these quantum dots. So in order to then tune the tip resonance to match this quantum dot resonance, we actually use as a free parameter the tilt angle of the tip. And we could show in previous work that depending on tilt angle, this defines a variable degree of confinement of this collective charge density oscillation in this tip apex region, and then allows us to control the field enhancement in this gap, as well as the spectral characteristics of this then out of plane localized surface plasmon resonance. So we'll match the tip angle to achieve a surface plasmon resonance of the gap, matching then the quantum dot resonance, and then we excite slightly blue detune from those resonances. And then we'll scan the surface looking for these individual quantum dots, and then observe their spectral emission, both when we are at few nanometer distances away, and then as we approach the surface, approaching the quantum dot, and then observing spectral modifications. So these are typical results. So we're seeing first, in the absence of the quantum dot, so the bare tip exhibits a plasmon resonance, which is evidence to a weak photoluminescence of the gold tip itself. We have the far field emission of the quantum dot in the absence of the tip. And then when the tip approaches the quantum dot, then we see tip-enhanced photoluminescence. So this is what we knew conventionally, and there is nothing exciting going on. As the tip approaches, the surface plasmon resonance actually slightly redshifts. This is due to dielectric effects increasing then the spectral overlap. When the tip is in very close proximity, when we really go into force interaction in the few nanometer to sub-nanometer regime with a quantum dot, then we see a qualitative change. We first see a dramatic increase in the photoluminescent yield, and then we'll see a very characteristic mode splitting of that cavity quantum dot emission. So then we want to analyze these data, and what we do is we use this conventional coupled oscillator model to describe strong coupling, which contains the terms for the plasmon resonance, as well as the quantum dot resonance with their respective relaxation, as well as this coupling term. And we can constrain both the resonant frequencies as well as the individual relaxation rates from fitting the data to the individual resonators from the quantum dot and the surface plasmon. And then with these input parameter, the fit you're seeing for this curve in the strong coupling regime is then only using the coupling rate as the only fit parameter. And so proportional to the Rabi splitting, then we can interpret these two peaks as the upper and lower polaritone band as they arise from the interaction of the plasmon and the exciton. What's also striking about these data is actually the purity of the signal in the absence of any significant background, which has been a challenge for a lot of previous experiments, especially when the quantum dots are not coded or embedded in any way. Then you get additional processes, you get charging, you get modifications of the quantum states itself to other peripheral processes. So we can then use this approach, and then we can study and now look at individual different quantum dots as they present themselves to us on the surface, as we simply scan the tip in force interaction to find a different emitter. So this is again the highlight here, is that we really can study and control then the emission of different quantum dots with the same tips. So we have the same cavity frequency, as you also see in the moment. And so then we can look at the inhomogeneous coupling strengths of this emitter to the different quantum dots. The quantum dots have slightly different local chemical environment, and also they have, because of their random orientation to the surface, different transition dipole moments. So the projection of this dipole moment with respect to the cavity field we can describe in combination with variations in this local environment through an effective tilt angle for this dipole. And then with this parameter, we can then fit emission where we actually don't observe strong coupling, which we interpret that the orientation of the dipole is in plane, and then various quantum dots where we achieve variable degree of coupling strengths, which we can describe through this effective tilting. The largest coupling strength we've observed is on the order of 180 millieV, and this is actually the largest coupling strength in any strong coupling experiments to our knowledge ever observed, and again at room temperature.
Professor, we have 2 questions.
Yeah, please.
Professor Weishan, you can go first. After Professor Hall, you can go after.
Hey, Max, this is really interesting. So could you go one slide back? Yeah, so I'm interested in this time variation, time domain trace. So it seems like there are time incidents that you don't see anything, and then all of a sudden, the strong coupling is back. And sometimes you only see the upper parietal or other than the lower parietal emission. Do you have any explanation for that?
Right. So these are details which are not readily really accessible to the experiment. So we do see, and that's why I show this, we do see slight spectral diffusion. And we do see occasionally the disappearance of any spectral signature, and occasionally we see a stronger or weaker relative response of the 2 polariton states. We don't really have a quantitative interpretation of this. We can only speculate that this is due to possibly either fluctuations, and I will show you the sensitivity in a moment, where we have about 0.2 nanometer noise in the tip sample distance. There is a possibility that we get slight reconfiguration of the atomic configuration of the tip. The gold is generally very soft. And then I imagine that we get charging of the quantum dot, that it resides temporarily in some dark state, but it always recovers. And so what you see here is a green curve is the time average over, say, 10, 15 second such measurement. But if we actually do measure this second and sub-second regime, we do see that there are these underlying fluctuations. And that's certainly interesting to study these further, but we don't have really a solid interpretation of this. Yeah, thank you for the question. Yeah.
Just one more follow-up question. So I imagine the quantum dots eventually would bleach, right? Would stop fluoresce under the strong coupling regime.
Actually, they don't. We can study the same quantum dot over multiple days. So the samples were stable over weeks. It's only now after a year where we looked at these samples again that most of the quantum dots have decayed in some fashion, but they are stable under this thin alumina layer. The alumina layer is not at 0.5 nanometer, not perfectly continuous. So this is porous. So there is a chance of oxidation and other processes, but otherwise they are stable for the course of weeks.
But do you know if the quantum dots is become more stable under the strong coupling condition compared to the weak coupling condition, like they less prone to be bleached or more prone to be bleached?
Yeah, that's an exciting question. But given that they live so long, we can only do an experiment for minutes at a time. So we couldn't really see, then it would be difficult to see a lifetime difference for those who have been subject to strong coupling and those who haven't.
I see. Thank you.
Well, hi. Just a very naive question. Can you explain experimentally if it's easy to change the frequency of the plasmons in the nanotip, and how is it like a very tunable parameter in your experiments?
So generally, I don't have an SEM image of a tip here, but generally the tips are etched electrochemically out of a gold wire, and the resonance is typically in this range between, say, 1.5 and 2 eV. That's where they come out, which is sensitive to sort of aspect, angle, and tip radius, and it's hard to control this in the chemical process. So the tip comes out in some way, and then we'll discover where the resonance is. The tip tilt does then tune the resonance over a few tenths of nanometer. So it allows them to further optimize the process, but it doesn't allow us to tune it over really a very wide spectral range. But generally, the combination then of selecting tip after etching plus some degree of optimization of the tip angle generally allows us to find an operating regime in that spectral range. And also, given the large line widths, it comes at an advantage here that we generally have within this Lorentzian tail enough spectral overlap to do an experiment and push it in the strong coupling regime.
And very quickly, following up on the observation that you were saying to not confuse these strong coupling line shapes with Fano line shapes. So can you elaborate a little bit more in your case, why are these not just Fano line shapes? So
we are in all these data. So what Pelton's work has distinguished here were linear scattering experiments. This is where in the coherent interaction you get a phase effect of the induced polarization, which can destructively interfere. And this gives rise to these, in this case, to these scattering spectra with the two peaks. But looking at the photoluminescence as the incoherent process, that is the critical signature that you do have splitting in the photoluminescent result. And here she shows an example where the scattering spectra are split, but there is no splitting in the photoluminescence.
I see.
And so all the data here are photoluminescence spectra. So always we don't do scattering, not linear scattering experiments. This is something which I will speak about in the infrared, where it's much harder, because in the infrared, we do not see IR photoluminescence out of the vibrational excitation. And so there we have to tease out and convince ourselves by other means that we are in the strong coupling regime when we do see complex line shape changes.
Thank you very much.
So you can continue now, Professor. Thank you very much.
Right. So I pick up where I stated that I think we have one of the largest coupling of single emitter. And associated with that is then two questions. One is the mode volume, and the other is, can we actually generate a tuning curve? And so here's again the typical set of data, which are fit under a constant plasmon resonance reflecting the tip pico-cavity. And from the fit, then we can see that we have different quantum dot resonances. And these quantum dot resonances we can then plot as a parameter described as a detuning. And then we can actually plot all data for all different quantum dots into a single graph, where we have different values for the coupling strengths, which gives rise to this series of anti-crossing curves, and these dots fall into different curves or different coupling strengths. And then within the range of their chemical heterogeneity and local variation, we have about 100 millieV spectral range of these different quantum dots. And this allows us then to achieve this anti-crossing spectrum. We can model these data then and describe this in sort of a three-dimensional plot, where we have one axis is the quantum dot detuning, and another axis is the coupling strengths, and then the energy values, and this gives you then these two anti-crossing spectral surfaces. The interesting question, which was already raised, is then how confined is the optical field, and what are the details of this transition then from the weak into the strong coupling regime. And so we can laterally scan the tip across the quantum dot, where as the tip approaches, it would interact then with a variable mode volume determined largely by the tip radius across this quantum dot. And so you start with the weak coupling when the tip is further away from the quantum dot, and as it approaches, the peaks start to split, and is maximum when the quantum dot is right under the tip apex. This process is typically over a distance given by the apex radius in the order of 10 to 50 nanometer. It's very different when you vertically approach the tip. In this case, you go initially from very modest but weak coupling because of just also small field enhancement. And then you get into the strong coupling regime over very short distances. So over a distance of only 3 nanometer, you really get with a gradient of tenths of millieV splitting per literally atomic radius which is on the order of 0.3 nanometers. So this would already correspond to a chain of gold atoms of 10 atoms as you are reducing that distance from a few nanometer just to residing then with the tip on the very top and close to the quantum dot. We can again plot these data then in a three-dimensional fashion where we evaluate the associated coupling strengths and its evolution then as a function of distance. And then you'll see that we get from a single unsplit peak evolving into a split peak, which in this case is on the order of 140 millieV as the maximum coupling strength. In collaboration with Matt Pelton, we have done theory and modeling of the associated mode volume, which is essentially a disc-shaped object right under that, right between the tip and the quantum dot, and we'll arrive at values on the order of 10 to the 4 cubic nanometers. So compared to the generally 10 to the 9 cubic nanometer you get for far field, this is what this nanoscopic mode volume looks like. So what these results show is really that we can do an active control of strong coupling of a single emitter. These results also point towards that we can really extend this to switch and modulate really single photon nonlinearities. We are currently working on experiments to show the single photon nature of this process as well. And then you can imagine that you can really do quantum state manipulation and entanglement, and all of this at room temperature, really extending experiments which traditionally have been able only at extreme cryogenic conditions. So let me ask if there are further questions about this electronic strong coupling, because in the second part now I will speak about cavity opto-mechanics, where we are looking at molecular vibrations and the progress and the perspective actually of why this is exciting to achieve that same goal of single emitter strong coupling also for molecular vibrations.
Yes, there is a question from Professor Gilad Haran. Let me allow your, yeah, you can talk now.
Yes, I would just like to comment that since you started with the brief history of quantum dot strong coupling, it's only fair to mention that there was a paper from 2016 by Santosh et al. At Nature Communications that was the first to introduce strong coupling with quantum dots.
Right. Yes, I'm familiar with this work. I just only showed a subset of those, and I also in your work, and there's a long list.
Since you said that the first one was hacked, I thought that I should correct it.
That was with the scanning probe approach. So where you use the same cavity for a different emitter. Yes, there were many previous experiments where people have done quantum dot strong coupling with plasmonic nanostructures.
No, there were actually not so many. But thank you.
Yeah.
Yes,
so, right. Are there other questions?
Yeah, there is another question in the chat. If you can read it, I can read it for you. What is the size or the radius of the tip apex?
So that varies. That also, depending on how the electrochemical etching works, it's between 5 and 10 nanometers.
Okay.
Right.
So it seems like there is no more questions, so you can continue. Oh, wait, there is another question. What is the quality factor of the cavities?
So the quality factor of the cavity is about 20 to 30. And that's determined by that's the line width of the plasmon resonance. And that corresponds to the usual tenths of femtosecond, 10 to 20 femtosecond combination of Drude and radiative relaxation of the plasmon resonance. So similar to what you get with other plasmonic nanostructures.
Okay, thank you very much.
All right. So the goal now is to explore the analog of the electronic strong coupling to do this with vibrational excitations of molecules. This is the idea, and this has also been highlighted in several previous discussions in this webinar on vibrational strong coupling. And it's an extension of work in cavity opto-mechanics, where people have the goal to achieve quantum transduction with membranes or surface acoustic waves between, for example, superconducting transmon qubits and other systems. And all these, of course, at these low frequencies where you have to be at extreme cryogenic temperatures in order to cool a macroscopic mechanical oscillator to the quantum ground state. If you could envision to extend this into the terahertz and the petahertz regime, which corresponds to the molecular oscillator, or correspondingly with the decrease of the mass, then with the associated energies, which would then allow you to be in the quantum ground state at room temperature. The other feature is that these systems are generally very harmonic. And so in order to potentially realize a qubit, then the feature of a vibrational oscillator is actually that we have an enharmonic bond potential. And so you could, by energy selection, really select a vibrational oscillator as a two-level system. And so this idea has been sort of conceptualized that as you are going down in mass of the oscillator, your mechanical frequency increases. And so as you achieve the mechanical, the mass and mechanical frequency of a vibrational oscillator, and then the idea that you can hybridize the state with a cavity. And this has been pursued to great extent very recently with ensembles of molecules in microcavities driving infrared vibrational excitations of these oscillators. Now, this area is actually converging with an area which actually started much earlier, about 20 years ago, which was because we have longer vibrational coherence time compared to electronic resonances, which are in the picosecond instead of the femtosecond regime, you could actually imagine to produce transients of the infrared driving field, which actually allow you to perform quantum operations even within this picosecond dynamics, where you prepare initial input states using shaped femtosecond pulses. And then with optimal control theory, it was actually shown already in 2002 that you can actually simulate a C0 gate through the coherent interaction of multiple vibrational oscillators. So we could envision a future by combining these different fields to actually imagine really quantum state manipulation and possibly even a qubit operation with molecular vibrations. So the way we do these experiments, we use infrared broadband femtosecond light sources. And now instead of looking at the photoluminescence, we actually look at the scattered emission out of the interaction of this vibrational driving field with a molecular oscillator. And then again, using the metallized scanning probe tip to localize this field into a nanoscopic mode volume. And then the measurement of the scattered field is a heterodyne detection of this field. And this gives rise then to free induction decay of this vibrational resonance, where the Fourier transform gives us then the complex value dielectric function with the resonance described through imaginary and real part, which can be associated with the absorption and the dispersion component of that spectrum. So we're applying this approach in a wide range of materials where we primarily image molecular, electronic, and photovoltaic systems and others, and study heterogeneity in functional materials. But then recently we were interested in whether we can push also this interaction in the strong coupling regime. In this kind of a warm-up experiment, what we started was looking now at metal nanowires on the surface, which are chemically functionalized in a very primitive way with a few nanometer thick polymethyl methacrylate, where we use this carbonyl vibrational resonance as it then interacts with this infrared antenna resonance at variable frequency. And what we observe is spectrally what's been expected. We see the usual phono interference of this vibrational oscillator with the antenna resonance. And so you see this visually here as we are imaging this antenna, where the tip here only acts really as a passive probe to provide spatial resolution. You see as we are tuning the wavelengths through this vibrational oscillator, especially antenna terminals, you get a brighter emission of this infrared scattered light. So we can then look at this dynamic interaction here in the time domain more closely. And then the first indicator of something interesting to happen is that we actually see a change in this vibrational lifetime depending on whether we tune the antenna resonance to be on resonance with the carbonyl resonance or whether we're off resonance. And so if you're on resonance, we have about 0.3 picosecond vibrational lifetime. And this is shorter than the off resonant interaction, which is essentially also the far field value of this 0.5 picosecond for this oscillator. And then we can tune the antenna resonance and evaluate these data quantitatively. And then we see that this relaxation time indeed has a minimum and is about a factor of 2 decreased compared to the corresponding far field uncoupled value. This is not strong coupling, but what this corresponds to is actually that we have Purcell-enhanced infrared emission. And this is illustrated here. What are the competing pathways, which will also inform us whether and how to get into the strong coupling regime. So generally in the infrared spectral range, you have very long radiative lifetimes. And this is because of the huge impedance mismatch of this atomic scale oscillator with these multiple micron long wavelengths. So we are here at 6 micron. And so what is traditionally in electronic transitions, nanosecond radiative lifetimes, as you get into the infrared turns into millisecond lifetimes. This is why generally for polyatomic systems, you never see infrared vibrational emission in the form of photoluminescence because of the inharmonic coupling of this vibrational mode manifold. You are dominated by typically picosecond scale intramolecular vibrational energy redistribution, which dissipates into heat before you have a photon emission. However, if you provide an infrared antenna and you have a coupling between this molecular oscillator and this antenna with a coupling rate which exceeds this non-radiative intramolecular loss rate, then you can envision opening a radiative pathway through a component of this antenna resonance decaying through a generally 10⁵ radiative lifetime, at least to some extent successfully competing against its own true relaxation into heat. So it's this pathway which we are looking for. And if we fit these data to a couple oscillator model, then we'll actually see indeed that we are arriving at an order of about 500 femtosecond coupling rate, which corresponds to about or is successfully competing against the intramolecular non-radiative molecular relaxation. And so we are actually transferring vibrational oscillator population into infrared radiation, which we don't see. In the coherent interaction which we probe, we don't probe this IR relaxation emission, but we are probing the change in this vibrational lifetime. And so this is an indirect indicator that we do open this pathway for radiation, and we can interpret this actually as a Purcell enhancement. And it's actually a gigantic value because from starting this coupling from initially 0 to a value to compete against this picosecond relaxation, then actually corresponds to a gigantic Purcell factor on the order of 10⁷. So this Purcell-enhanced emission is already interesting. You could imagine push this in sensitivity to achieve single molecule spectroscopy. One can use this with the idea to use molecules as IR emitter and can envision already some form of quantum state transfer. And it would point the way towards the strong coupling regime. But to do that, we have to really achieve something which has been, yes?
I'm sorry, Professor. Yeah, there is a question from Professor Blaise Simpkins. Yeah, so
yeah, hi, thank you. Great stuff. I have a question on the previous slide. This 500 femtosecond timescale for the molecule. This is if I understand correctly, a population lifetime.
Right.
And and this is kind of a weak coupling regime.
Yes.
As you look forward and push this into a strong coupling regime, would it instead be the dephasing lifetime of the molecule that matters, or can you discuss those two lifetimes and how they matter?
So what we would need to exceed to achieve the strong coupling is that we would need to have this coupling rate then not simply exceed all the molecular relaxation pathways, but also all the dissipation pathways of the coupled antenna system. And so we need to exceed either the 10th of femtosecond Drude relaxation of a localized antenna resonance, or if you go to some photonic modes with some meta surface, then we would need to exceed where we can have longer plasmon resonant lifetimes, but then at the expense of mode volume. And I'll get to that actually in a moment, how we're trying to sort of box this problem in with different approaches.
Okay, thanks. I was a little more interested in the dephasing of the molecules. Since they can be quite fast, will it be problematic to see an enhancement of molecular response?
So generally, a molecular oscillator does not show pure dephasing. So this population lifetime is this factor of 2 related generally to the molecular coherence time. The main thing we need to consider, though, is also that we have inhomogeneous broadening for these molecular oscillators, and this is why we are going to monolayer and trying to get very controlled nanocrystals of molecules where we have reduced decoherence from inhomogeneous broadening.
Excellent, thanks.
Hello. Sorry, I just want to follow up on the discussion that you had on Fano versus strong coupling, and then the fact that you say that you monitor this strong coupling through scattering. So can you elaborate what are the? So I'm sure you already mentioned this, but can you elaborate again? What are the hints in the experimental signatures of this scattering that allow you to conclude that this is strong coupling again?
Right. So I will get to this. So this is weak coupling. There is no indication of strong coupling.
Okay.
These spectral line shapes, and I'll show you more of these in a moment, which we achieve plenty of, can all be explained through to Fano interference between the antenna resonance. So I'll show you more data, and then I'll actually show you already on the next slide what is a signature of strong coupling in molecular vibrations. So maybe let me continue on, and I'll get back to your question when I show more data. So the signature for strong.
Just a quick one more question. Do you think it would be possible to actually measure the IR emission directly?
Yes, we believe so. The hard part is to distinguish it from the direct coherent scattering response. But there are ways how you can do this. And this is also when we get to smaller ensembles, possibly to the single molecule response, how we can then with short pulse excitation and then monitor time resolved the IR emission. There is an effort with collaborators at NIST to push this to single photon IR detectors. Then one could envision this, yeah. But it's hard. And we don't have answers to all the problems we have. So I really appreciate this community, and we're really open to collaboration. So any solution to any problem, we're open to it. Yeah.
Well, what would be the expected quantum yield of the emission?
So it is low, depending on how effective we can outcompete the intermolecular vibrational energy redistribution into heat. So if this coupling between the antenna mode and the molecule, if we can get this larger, and we don't know yet how to do this, then you can have high quantum yields. And the feature is that the antenna coupling, in some way, this is where the long spontaneous emission time in this millisecond range. This is why also in gas phase, you have very narrow vibrational resonances for small molecules, that you actually have a chance to open such a pathway, because the molecule tends not to emit radiatively otherwise. So the processes that we are aiming for, and I'll show this in the summary then again, that we are aiming to already look for oscillators which have intrinsically longer vibrational lifetimes, where the oscillator is weakly coupled to the polyatomic many-body manifold.
Okay, I think you can continue now.
So the simple hallmark for vibrational strong coupling is actually an infrared absorption experiment where you put, and this is how it's done by a number of practitioners, where you put an ensemble of molecules in a microcavity, and then the resulting hybrid state gives rise to the vibrational coupling of these two states. And doing these experiments carefully in these microcavities, then there is limited alternative interpretations for artifacts. And so this is a very clear signature of strong coupling of these ensembles. And as many of you know, and this has been discussed in previous meetings, that there is a wide range of possible applications from quantum nanophotonic to photochemistry, and even the idea of actually vibrational lasing and parametric generation in strongly coupled ensemble molecules in cavities. So the goal would then be, can we achieve the same in pico-cavities, pushing then to smaller and smaller ensembles, with the big vision, of course, whether one can manipulate ultimately a single vibrational oscillator at infrared frequencies in strong coupling. And so one of the routes we have been considering was that, as I showed you previously, with the Purcell-enhanced emission or Purcell-enhanced molecular coupling, that the single antenna is insufficient to couple strongly enough to molecular vibration. And so there has been an interesting avenue which emerged several years ago, and this was an analog to push to a 3-resonator system, where one component or related aspect of strong coupling is actually to demonstrate electromagnetically induced transparency and absorption as examples of a system where you modify the coupled emitter. And so this was demonstrated in 3 or multiple resonator systems from microwave and also in the infrared. So our goal was then to combine the optical scanning probe tip, providing then the transduction of this incident infrared field, coupling it into an infrared antenna mode on a engineered sample, and that coupling itself then to the vibrational oscillator, where we typically functionalize these antennas with molecular monolayer or a thin layer of spin-coated molecules. And so this 3-level or 3 oscillator system then consists of a broadband of a localized infrared antenna resonant nanowire. It consists of the molecular oscillator, and it consists of the scanning probe tip, which in this case is much harder to engineer to actually have a narrow resonance. So this is generally, for these experiments, a broadband oscillator. And then in these experiments, we routinely see in the tip scattered signature split peaks, as well as when we tune the nanowire antenna, then we get these anti-crossing behavior. However, all these data can be perfectly fit with a Fano behavior, all due to the coherent interaction and interference of the molecular oscillator with the nanowire. But we can quantify in these experiments the different coupling rates, the coupling of the nanowire to the molecular vibration, as well as to the tip, as well as the wire to the tip. And a feature in these experiments is that as we are changing the position of the tip relative to the nanowire, we can change the relative phase of these fields which drive the molecule, whether it is through the antenna wire itself, or depending on tip position, where we get a phase difference in the coupling of the tip to the wire and to the molecule. And so this is how we can then use this as a simulator to demonstrate that in these experiments we can actually achieve electromagnetically induced absorption or transparency, but it's a scattering experiment. It would be then electromagnetically induced scattering. So in quantifying these coupling terms, then we can show that the nanowire vibration coupling is on the order of a few tenths of wave number, 50. The tip nanowire coupling depends on the position of the tip to the nanowire is in similar quantity, and this allows us for this vibrational phase control. I'll see we are running out of time, so let me try to actually cut to the chase here. Then in order to achieve strong coupling, we have to reduce the antenna damping. So these coupling rates I just showed you are still insufficient to achieve enough coupling to outperform the relaxation of the system. We can't even quite outperform the relaxation of the molecular vibrational lifetime, which is on the order of 20 wave number. So what we do is the first step in these experiments is that we actually go to a dark mode antenna. So we start by taking nanowires antenna where we turn off their radiative emission. And if you go to these dark mode antennas, they are not far field active. So their resonance is only appearing in a near field coupled experiment. So only when the tip interacts with the nanowire can we actually couple light into the system. And this is shown here, comparing the far field modes of these antenna wires, where you have the ground state mode, we have the second and the third, and the second mode is not far field active, but as the blue curve shows, only in a near field experiment, we can excite this. So if you then look at the tip scattered vibrational emission, then we see a qualitative change in the spectra. Instead of this simple split, and now we actually see a peak emission in particular, for a particular coupling strength. And if we fit these data, now we can show that now we have a tip vibration induced coupling at a rate which is now exceeding the intrinsic vibrational life or coherence time on the order of 20 femtoseconds. And so this is still not in the fully strong coupling regime because the lifetime of the vibrational, of the electronic resonance of the antenna is still shorter than these few picosecond, but it points in the right direction, and these dark mode antennas do have longer vibrational lifetimes. So this at least gives us a roadmap where these spectral modifications, as we see compared to the simple Purcell-enhanced emission, already point towards that we are reaching a transition regime into strong coupling, but we are not there yet. So with that, I'd like to sort of summarize a couple of avenues we are pursuing. So one is to look at vibrational oscillator, which have very long intrinsic vibrational lifetimes. Systems of interest are surface decorated molecules, for example, hydrogen and silicon has a very long vibrational life and coherence time. And this is because this SIH oscillator is very decoupled from these from the phonon bath. And other systems are isolated small molecules, for example, in the lattice. These are water molecules in the barrel. Is a natural mineral which has these open pores. So going to small molecules which are weakly coupled to their local chemical environment, then you can imagine that you fully take advantage of these very long and then actually vibration and radiation damped molecular oscillators in a solid state environment. Other directions are carbonyl oscillators in ruthenium metal carbonyls. We currently have experiments underway where we use molecular monolayer, which we can also dilute so that we can push also into the single molecule regime. And that itself would be a goal, even if you can achieve this outside the strong coupling regime. One question which was raised earlier was also, how do we detect light? Currently, the heterodyne amplification is very powerful, but alternatives are actually using frequency combs and electro-optic sampling, in addition to developments, which is a multi-year effort to think about vibrational or single molecule detectors, as single photon detectors in the mid-IR based on superconducting nanowires. And so that will lead to the question then also, can we achieve ultra-fast control of these coupled vibrations? A parallel effort, which was work in collaboration also with Mikhail Belkin, it was on doing the analog in the infrared, but not on molecular vibrations, but doing this on inter-subband transitions in infrared quantum wells, where again, benefiting from the strong transition dipole moment in these systems, we were actually able to show strong coupling and even switching on ultra-fast timescales of quantum well transition in the mid-infrared. So this is informing us and helping us shaping the questions, because then also in these experiments we observe scattering out of the near field coupled mode volume. And then recent work, and this was presented at this meeting, and I want to just thank for this collaboration again with Sang-Yuk Oh, was further controlling mode volume and using meta surfaces where we can potentially engineer that we have very small mode volumes in engineered meta surfaces, which then have long coherence times, and then combining these with tip localization so that we can localize small ensemble or even few emitter and achieve this ultimate goal of single emitter vibrational strong coupling. So with that, I'd like to conclude and thank everyone for their attention, and I really appreciate these questions. I'm very open for collaborations and further input. So please let us know where we need to correct our approach, and thank you so much.
Thank you very much, Professor Markus Raschke. I don't see any more questions from the audience. So I guess I do have one more question though. In the first part of your talk, you talked about strong coupling with these plasmonic nanoparticles in the electron volts energy regime. But if you try to make electronic strong coupling with molecules, what would be the extra complications you would find there in that case?
So this is an attractive feature, and we'll like to do this because then also we get smaller mode volumes compared to the larger quantum dots. I think the main question is that we need to protect the molecules from photobleaching. And so different ideas are discussed, embedding them in the polymer matrix, and those things have been tried. And I think this is sort of for us also a way to go, also combining this with self-assembly strategies, so there would be benefits. They would have somewhat weaker transition dipole moment, but the smaller mode volume could well compensate for that if we can avoid photobleaching, get stable interaction with the molecule.
Okay, thank you very much again for a great presentation. Thank you everyone who attended the webinar. Let me just share my screen for a bit to tell you that next week we will have Professor Barbara Pietka from University of Warsaw, who's going to talk about real magnetic fields and artificial Hamiltonians to control exciton polarity and spins. So thank you everyone. I hope to see you next week.
All right, thank you.